Ladies and gentlemen, imagine a world where machines don't just follow orders. They learn, adapt, and work alongside us like never before. Picture robots that can carry, build, and even think through complex tasks with human-like precision. What was once science fiction is now rolling off production lines, gaining intelligence with every movement, every task, every moment. Today we stand at the edge of a revolution in robotics, a moment where technology stops being a tool and starts being a partner. Stay with us because what you're about to see is not just the future, it's happening right now. The latest production update signals a decisive step forward in the evolution of intelligent robotics rooted in the same first principles, thinking that reshaped electric vehicles, energy storage, and autonomous systems. This update reflects a shift from experimentation to scalable manufacturing where software, hardware, and real-world data converge into a unified platform designed for reliability, efficiency, and rapid iteration. The focus is no longer on what a humanoid robot might do in the future, but on what it is already learning to do today inside controlled environments that mirror real-world complexity. And at the core of this progress is a vertically integrated approach. By designing custom actuators, sensors, batteries, and neural networks in-house, the production pipeline remains tightly optimized. Each component is engineered with cost, durability, and performance in mind, allowing improvements to cascade across the entire system. Advances in electric motor efficiency, lightweight materials, and energy density directly translate into longer operational time and smoother, more human-like motion. These gains are not theoretical. They are validated through continuous testing and rapid deployment cycles. And equally critical is the software foundation. The robot leverages the same AI architecture philosophy used in large-scale autonomous systems, relying on vision-based perception, end-to-end neural networks, and massive data training. Cameras and sensors feed real-time information into onboard compute, enabling the system to understand space objects and tasks without reliance on pre-programmed scripts. Each production unit contributes data back into the training loop, accelerating collective learning and reducing edge cases over time. This creates a feedback-driven manufacturing model where every update compounds progress. And the production update also emphasizes manufacturability at scale. Lessons learned from high-volume vehicle production inform the assembly process, from modular design to automated quality checks. Simplifying parts, reducing wiring complexity, and standardizing interfaces allow faster build times while maintaining precision. Factories are being adapted to accommodate robotic assembly lines that mirror the efficiency of existing manufacturing operations, ensuring that increased output does not compromise consistency or safety. And another major development highlighted in the update is task specialization. Early production units are being trained on practical, repeatable activities, such as material handling, object sorting, and basic assembly support. These tasks are deliberately chosen for their immediate value in industrial settings where repetitive manual labor can be physically demanding or inefficient. By deploying robots in these roles, human workers are free to focus on higher-level problem-solving, oversight, and creative work. This collaborative model underscores a broader vision of augmentation rather than replacement. And safety and reliability remain central priorities. Each production iteration undergoes rigorous validation, including redundancy checks, fail-safe mechanisms, and controlled environment testing. The robot is designed to operate with a clear understanding of force limits, balance, and spatial awareness, minimizing risk when working alongside people. Continuous over-the-air updates allow improvements to be rolled out quickly, ensuring that safety enhancements evolve in step with capability upgrades. And cost reduction is another theme running through the production update. By applying economies of scale, simplifying designs, and leveraging shared technology platforms, the long-term goal is affordability without sacrificing performance. This mirrors the trajectory followed in electric vehicles, where early prototypes paved the way for mass-market accessibility. As production ramps, each unit becomes not only more capable, but also more economical to produce, opening the door to wider adoption across industries. And taken together, this production update represents a transition from concept to execution. It demonstrates how disciplined engineering, data-driven AI, and manufacturing expertise can converge to build a new class of intelligent machines. The emphasis on scalability, real-world utility, and continuous improvement signals a future where humanoid robotics becomes an integral part of daily operations, learning, adapting, and delivering value at a pace defined by software iteration rather than traditional hardware constraints. And this momentum is further reinforced by the way real-world deployment feeds directly back into development. As production units operate in controlled facilities, warehouses, and pilot manufacturing lines, they encounter thousands of micro-variations in objects, surfaces, lighting, and human interaction. Each of these interactions becomes training material, strengthening perception, dexterity, and decision-making. The result is a system that improves not in isolated lab conditions, but in environments that reflect the unpredictability of daily work. This approach accelerates capability growth, while keeping improvements grounded in practical use. And energy management plays a pivotal role in this phase of expansion. Battery architecture has been refined to balance power output, longevity, and thermal stability within a compact form factor. Intelligent energy allocation allows the robot to dynamically adjust consumption based on task complexity, movement intensity, and idle states. This ensures consistent performance across long shifts while minimizing downtime. Charging systems are being optimized for rapid turnaround, drawing from existing energy infrastructure expertise to integrate seamlessly into industrial workflows. And motion and manipulation have also advanced significantly. Fine motor control, once a limiting factor, now benefits from high-fidelity torque sensing and adaptive grip algorithms. The robot can modulate force in real time, enabling it to handle delicate components as confidently as heavier loads. This versatility expands the range of viable tasks from precision placement to bulk material transport. Continuous refinement of joint design and balance control contributes to smoother movement, reducing wear and improving long-term reliability. And another important element of the update is the emphasis on learning by observation. The system can analyze human demonstrations, translating visual input into actionable sequences without extensive manual programming. This dramatically shortens the time required to introduce new tasks and allows rapid customization for different environments. Combined with reinforcement learning, the robot can iterate on these demonstrations, optimizing efficiency and accuracy through repeated execution. And manufacturing alignment remains a key differentiator. By using the same factory's supply chains and automation strategies that support other advanced products' production scales without reinventing infrastructure. This shared ecosystem enables faster iteration cycles where design tweaks can be implemented, tested, and refined with minimal delay. Quality control benefits from automated inspection systems that flag inconsistencies early, maintaining tight tolerances even as volumes increase. And the update also highlights progress in human-robot interaction. Natural movement patterns, improved spatial awareness, and responsive behavior make collaboration more intuitive. Visual cues and contextual understanding allow the robot to anticipate human actions, reducing friction in shared workspaces. This is critical for environments where efficiency depends on seamless coordination rather than rigid separation between humans and machines. And from an economic perspective, early deployments provide measurable insights into productivity gains, injury reduction, and operational efficiency. These metrics guide further refinement, ensuring that each iteration delivers tangible value. The long-term vision centers on creating a platform that can be adapted across industries, from manufacturing and logistics to services and maintenance, without fundamental redesign. And scalability extends beyond hardware into software distribution. Over-the-air updates enable synchronized improvements across the entire deployed fleet, allowing new capabilities to propagate instantly. This transforms each robot into part of a collective system where learning is shared and progress compounds globally. Security and data integrity are built into this process, ensuring that updates enhance performance without compromising reliability. And as production continues to ramp, the focus remains on disciplined execution. Incremental improvements validated by data and real-world use define the development rhythm. Rather than chasing speculative features, the roadmap prioritizes capabilities that solve immediate problems while laying the foundation for more complex autonomy. This methodical approach ensures steady progress, aligning innovation with manufacturability and deployment readiness. And the expanding production footprint reflects confidence in this trajectory. Facilities are being prepared to handle higher volumes, suppliers are aligning with tighter specifications, and automation is increasing across assembly lines. Each step reinforces the central objective of delivering intelligent, adaptable robots at scale, guided by the same principles that have driven advancements across multiple technology domains. And this trajectory continues to be shaped by a deep emphasis on data efficiency and continuous learning. As deployment scales, the system is exposed to an ever-growing diversity of scenarios, allowing neural networks to generalize faster and with greater confidence. Rather than relying on narrowly defined task boundaries, the robot develops a broader understanding of cause and effect, spatial relationships, and object behavior. This enables smoother transitions between tasks and more resilient performance when conditions change unexpectedly, such as altered layouts, new tools, or variations in materials. And sensor fusion plays an increasingly important role in this stage of development. Vision remains the primary input, but it is complemented by proprioceptive feedback, tactile sensing, and real-time force monitoring. This layered perception allows the robot to build a richer internal model of its surroundings and its own physical state. Subtle adjustments in posture, grip, and balance happen continuously, creating movement that is both efficient and stable. These refinements reduce error rates and improve consistency, which is essential for environments that demand precision at scale. And the production update also reflects progress in autonomy at the system level. Task planning is becoming more adaptive, with the ability to sequence actions based on real-time feedback rather than fixed instructions. When an obstacle appears or a task parameter changes, the system can reevaluate and adjust without external intervention. This reduces downtime and increases overall throughput, particularly in dynamic environments where variability is the norm rather than the exception. And workforce integration remains a guiding principle. Training programs and deployment strategies are designed to ensure that robots are intuitive to work alongside, requiring minimal supervision. Interfaces are streamlined, allowing operators to assign tasks, monitor performance, and intervene only when necessary. This lowers the barrier to adoption and accelerates real-world impact, as organizations can integrate robotic assistance without extensive retraining or infrastructure changes. And reliability at scale continues to be validated through stress testing and long-duration operation. Components are evaluated for wear under continuous use, and predictive maintenance models are refined using operational data. By identifying patterns that precede component degradation, maintenance can be scheduled proactively, reducing unexpected interruptions. This approach mirrors established practices in other high-reliability systems where uptime and consistency are critical metrics. And supply chain optimization is another area of ongoing focus. Standardizing components across platforms simplifies sourcing and improves resilience against disruptions. Close collaboration with suppliers ensures that materials and processes meet increasingly stringent requirements, supporting both quality and volume targets. This alignment allows production to scale smoothly while maintaining tight control over performance characteristics. And the update also underscores advancements in simulation and digital modeling. High-fidelity virtual environments are used to test new behaviors, validate updates, and identify edge cases before deployment. These simulations replicate real-world physics and variability, allowing rapid experimentation without risking hardware. Insights gained in simulation are then transferred to physical units, shortening development cycles and reducing iteration costs. And ethical and practical considerations remain embedded in the design philosophy. The system is engineered to operate transparently with predictable behavior and clear boundaries. Safeguards are continuously refined to ensure that interactions remain safe and controlled, particularly in shared spaces. This focus builds trust and supports broader acceptance as deployment expands beyond controlled pilot environments. And as capabilities grow, the platform approach becomes more evident. Hardware improvements, software updates, and new task modules can be layered onto existing units, extending their usefulness over time. This modularity ensures that early deployments remain relevant as technology advances, reinforcing long-term value and sustainability. And the scaling process reflects a balance between ambition and discipline. Each increase in volume is matched with rigorous validation, ensuring that performance, safety, and reliability keep pace. This steady progression demonstrates how complex robotic systems can move from prototype to production without sacrificing core principles. By grounding innovation in real-world data and manufacturing expertise, the program continues to advance toward broader deployment, with each iteration building upon a foundation of measured, repeatable progress. And this momentum opens the door to broader functional intelligence, where the robot begins to understand not just how to perform tasks, but why they are performed in a certain sequence. Context awareness is becoming more refined, allowing actions to be prioritized based on efficiency, safety, and real-time objectives. Instead of treating each instruction as an isolated command, the system interprets tasks as part of a larger workflow, optimizing movement and timing across an entire process. This reduces redundancy and enables smoother coordination within complex operational environments. And learning scalability remains a defining advantage. When a single unit masters a new behavior or resolves an edge case, that knowledge can be propagated across the entire fleet. This collective intelligence model means improvements no longer happen linearly but exponentially. Each deployment strengthens the network, and each update elevates baseline capability. Over time, this creates a compounding effect where progress accelerates as more units come online and contribute data. And hardware evolution continues in parallel with software growth. Structural components are being optimized for strength-to-weight efficiency, improving agility without sacrificing durability. Thermal management systems have been refined to maintain consistent performance under sustained workloads, ensuring that computation and actuation remain stable, even during extended operation. These refinements directly support higher duty cycles and broaden the range of viable use cases. And dexterity is advancing beyond simple manipulation into coordinated multi-step interaction. The robot can now manage tool usage with increasing confidence, adapting grip strategies based on object geometry and task requirements. This capability is essential for environments where tools vary widely and precision is critical. The ability to transition seamlessly between freehand tasks and tool-assisted actions significantly expands functional scope. And another focus area highlighted by this stage of development is environmental adaptability. The system can adjust behavior based on surface conditions, spatial constraints, and dynamic obstacles. Whether navigating tight spaces or operating on uneven ground, balance and locomotion algorithms continuously adapt to maintain stability. This flexibility allows deployment across a wider range of facilities without extensive customization. And human collaboration continues to evolve through more natural interaction patterns. Predictive motion modeling enables the robot to anticipate nearby human movement, reducing pauses and unnecessary spacing. This leads to more fluid teamwork where robots and people operate side by side with minimal disruption. Over time, this familiarity fosters trust and efficiency, transforming robots from tools into collaborative partners. And operational intelligence is further enhanced through analytics and monitoring. Performance data is aggregated to identify bottlenecks, inefficiencies, and opportunities for improvement. These insights inform both software updates and hardware revisions, creating a closed-loop optimization cycle. Decision-makers gain visibility into productivity gains and operational impact, supporting data-driven scaling strategies. And global deployment considerations are also being addressed. Localization for different regulatory environments, workplace standards, and cultural expectations is built into the platform design. This ensures that expansion into new regions can occur smoothly with compliance and adaptability handled at the system level rather than through custom builds. And sustainability remains integrated into long-term planning. Energy-efficient components, recyclable materials, and extended product life cycles reduce environmental impact. By designing robots that can evolve through updates, rather than replacement, resource consumption is minimized while value is maximized. This approach aligns technological advancement with responsible manufacturing practices. And as production capacity increases, coordination between engineering, manufacturing, and deployment teams becomes even more critical. Feedback loops tighten, iteration speeds increase, and the gap between development and real-world application continues to shrink. Each cycle reinforces a disciplined approach where innovation is guided by data, execution is grounded in manufacturability, and progress is measured by real-world outcomes rather than speculative benchmarks.